Welcome back to our video lecture series on the material science and metallurgy subject. Today's topic is on crystallographic points, and this is an overview of today's presentation. So, briefly we will introduce about the importance of studying about crystallographic points. Then how do you represent these crystallographic points within the crystal structure. Then some of the exercise problems we will see, 1 or 2 exercise problems. Then finally we will summarize what we have discussed in today's class. In the last class we have discussed various crystal structures and calculation of APF factors for that crystal structures. Crystal structures like a simple cubic crystal structure, body centered cubic crystal structure, face centered cubic crystal structure, and HCP, hexagonal close packed structures. We have discussed about it, how the atoms are positioned within these crystal structures, as well as what is a coordination numbers and what is a lattice constant and radii of atom, the relationship between them, and then packing factor or packing density, atomic packing density. We have calculated these values for all the crystal structures, right. So, when you are working with these crystalline materials, metallic crystalline materials to be precise, so it is frequently necessary to specify a particular point within a unit cell. You may come across it is frequently necessary to point out a specific point within a unit cell or a particular direction, a particular crystallographic direction you may need to specify, or you may need to specify a particular crystallographic plane. So, when as we have studied these properties of metallic crystal material, most of the materials, metallic materials, it is dependent on crystal structure as well. So, some of the properties that are majorly dependent on crystalline structure and how they will influence properties of the material, we have discussed it in our previous classes. So, when you are discussing about the atomic arrangement within this crystal structure, it is always there could be a chance that the positioning of these atoms precisely at particular location, or if you wanted to talk about atoms which are specified in one particular direction, any that is parallel to any one of the axes or inclined to any one of the axis, any particular direction you wanted to talk about it, atoms that are aligned within that direction, or if you wanted to specifically talk about the atoms that are present on a particular plane. So, first of all we have to know how do we represent these points within this crystal structure. So, a labeling convention is very much required to represent these crystallographic points or crystallographic directions or crystallographic planes. So, that labeling conventions are to be established. So, that need to be a 3 number or 3 indices. And how do we get these indices? Yes, our unit cell is a fundamental building block for any crystal structure. So, that unit cell serves as the foundation for determining these indices. What are these indices? We are talking about these 3 indices. The foundation is your unit cell will become your foundation, and we will be considering a right hand coordinate system here. So, which is having 3 axes, x, y, z, 3 axes, where it is located at the corners. So, at one of the corner we will be taking the origin point in the unit cell, and coinciding with this the unit cell edges, we will be drafting the 3 axes x, y, and z, and this is how we will be start labeling the crystallographic points or directions or planes. Let us look at how these crystallographic points will be labeled. So, for that we will take one of the examples. So, in the figure in the image you can see there is a unit cell. So, this is a unit cell. So, this is your unit cell, right, and then you are having a coordinate system. So, here is your origin, okay. So this is your origin point, right? Then this is your x-axis, then in this direction. So in this direction you have y-axis, and in this direction you are considering the z-axis, the right hand coordinate system, x, y, z coordinate system we have taken. And the point of our interest, or the point for which you have to represent the three coordinates, three indices or the three numbers, is this is a point. So for this point P, I wanted to have, I wanted to locate these indices, right? I wanted to represent this point P within this unit cell, right? So how do we do that? So let us assume this is a lattice constant, that is a edge length of the unit cell, that is in x direction you have lattice constant A, in y direction it is B, and in the z direction that is C. Three edge lengths in the x direction, y direction and z direction, A, B, C. And here we will be considering how do we position any point within the unit cell. So we position, so with respect to, it will be specified in terms of its coordinates, that is x, y, z coordinates, as the fractional multiples of the unit cell edge lengths, as the fractional multiples of unit cell edge lengths. What are these unit cell edge lengths? That are A, B and C. So for what are these fractions, fractional multiples for A, fractional multiple for A, that is a Q here in this case. And in the case of B, so that is fractional multiple is R, and in the case of C, that is a fractional multiple is S. So what are these indices? That is Q, R, S. So in the edge length A, that is Q, and in the edge length B, that is R, and in the edge length C, that we have the S, and these are the three indices for locating a particular point. So based on this three fractional multiples of unit cell edge lengths, we specify particular point within the unit cell. So position of P is designated using the coordinates, that is Q or S, with the values that are less than or equal to unity, right? This is a fractional multiple, so maximum it will be having that is equal to your edge length, that is A. So if it is A, then the fractional multiple that will be unity or equal to 1. Okay, so always it could be less than this edge length, less than this edge length. So your fractional multiple will be less than 1. So the values of three indices Q or S, that will be either that is equal to 1 or it will be less than 1, less than the unity. Let us pick one example and we will see. So this is your unit cell, how to draw. So this is your unit cell, a cube, and I have located origin. So here is my origin. Then here I am drawing the three coordinates, that is the x and then the y, then we have the z, three coordinates. Then where is my point? Point P. This is my point P. For this particular point P, I have to locate the point P within this unit cell. How do I get it? So I have to go back. How this has been drawn. So I have to go back in the z direction. I have to go back in the y direction. So let us say, and then it will be going back in the x direction. Let us pick it. So let us see how we will be drawing it. So this point P, so that is the with respect to z coordinate. So we will be taking the point, and then we'll be moving back in the y direction. So this is in the y direction, and this is in the z direction. We are dropping the points with respect to the coordinates. We are looking at the fraction. Then similarly in the x direction, right? This is in the x direction. So we have to find out these fractional multiples. So first, what is this? This is the edge length A in the x direction. So what is this? This will be, what is the distance? This could be, so this could be a portion of A, right? This could be a portion of A. So this, what is that portion? That is a Q. Q is a portion. So then similarly in the y direction unit cell, we have the edge length, that is B. So in the y direction, so what is this portion? So this is the edge length, the total edge length is B, but this is just a portion, it is not a complete B, right? It is a fraction, it is a portion only, some portion. So what is this portion? That is R. Similarly in the z direction, what is the edge length? The total edge length, that is a C. This is a complete C, but this is just a portion of C. So what is this fraction or the portion? That is represented with respect to S, right? So this is how we will be having, so the x direction portion, y direction portion, and in the z direction portion, that is Q, R, S. These are the indices. The position of the P, that is specified in terms of the coordinates as the fractional multiples of unit cell edge length. So QRS will be less than or equal to 1. So take one exercise problem. So a question is given. So for the unit cell shown in the accompanying sketch, then locate the point having coordinates 1 by 4, 1 and 1 by 2. So it is nothing but this is a Q and this is R and this is S. QRS. So QRS points are given. Now we have to locate the point, right? So what is A here? So it is in the x direction. So this is your A. And what is B here? What is B? B is this one. And what is C? C is this one. So what is A? A, that is equal to 0.48 nanometers. And B, that is equal to 0.46, and C, that is equal to 0.4. So how do I locate it? So fractions we know, okay. Position of the point we have to now write it out. Position of the point, so position we have to consider. Position of point P, so in the x direction. How do we get it? We have to, that is nothing but Q multiplied by A, right? QA. So what is Q? We have 1 by 4 multiplied by what is A? 0.48. So what is this value? This is nothing but 0.12 nanometers. And similarly in the y direction, so y direction, what is a fractional multiple? That is R. What is the edge length? That is B, RB. So what is R1? 1 multiplied by 0.46. It is nothing but 0.46 nanometers. Similarly in the z direction, if I calculate, so what is fraction? That is S multiplied by C, that is equal to 1 by 2 multiplied by 0.4. Right? 1 by 2 multiplied by 0.4, nothing but 1 by 2 multiplied by 0.4, that is nothing but 0.2 nanometers. So we got the position in the x direction, that is 0.12, position in the y direction, that is 0.46, position in the z direction, that is 0.12. So how do I locate it? So this is my origin point, okay. So I have to move it, I have to move in the x direction by how much? 0.12. So this is 1/4. So if I divide by, this is half and this is 1/4. Let us take, this is a point. I have moved with respect to x direction by 1/4. And in the y direction, I have to move it complete y direction. So if I move it complete y direction, so that is somewhere here. So I have moved in the y direction as well. In the z direction, how much it need to go? So half of the total length. So this is the half, and if I draw a perpendicular, or if I draw a line parallel to this, so this is the half. So this is a position P, which is having 1 by 4, 1, 1 by 2 as a indices. That is a point P. That is how we have to locate point P, right? So this is how, this is the solution, final solution. We have moved in the x direction by 0.12 nanometers, and we have moved in the y direction by complete edge length, that is 0.46 nanometers, and we have moved in the z direction by about half of the edge length, that is 0.2 nanometers, and this is your point P, right? That is your point P, which is having coordinates of 1 by 4, 1, 1 by 2, right? Similarly, we will look at exercise problem number 2. So here is a question: specify point coordinates for all atom positions for a BCC unit cell. BCC nothing but body centered cubic crystal structure, BCC unit cell. So if I take the body centered unit cell, so how many atoms will be there? We know that each corner we will be having 8 corners, 8 atoms will be there, and at the center of the unit cell, at the center of the unit cell we will be having one complete atom, that is a body centered atom. So corner atoms 1, 2, 3, 4 I have taken, and this is a center atom, that is a fifth one, and 6, 7, 8, 9. So these are the total atoms within the BCC unit cell. So for all these 9 atoms, we have to now provide point coordinates, right? Point coordinates with respect to x, y and z coordinate system. So let us start from the 1. So point 1. So point 1 is just at the origin. So here is origin. So at the origin, what will be the coordinates? The multiples of A. So that will be absolutely multiple of A, that is 0. And multiple of y also, that is 0, and multiple of z is also 0. So it is, the coordinates is nothing but 0, 0 and 0 for the atom position 1. So we will try to tabulate one atom. So in the x, y and z, if I take it, so in the x that is 0, and y that is 0, and z is also 0. Similarly, if I take the second atom, what is the x coordinate? So second atom, the x coordinate is, it has moved by a distance. So what is a fraction? So it is moved by a. So moved by a by a, the fraction will become 1. So moved by 1 unit, right? So it is moved by 1 complete unit. Then what is the x, y? There is no movement in the y. So there is no y. That will be 0, and there will be no z also, so that will be 0. So what is the coordinates for this? 1, 0, 0, and for this 0, 0, 0. And similarly 3, atom number 3. How do I calculate? So atom number 3, I have moved by 1 unit here, and I have moved by another in this. So there is this in the x direction we have moved by 1. And in the y direction also we are moved by 1. In the z direction there is no movement in the z direction. So the coordinates will become 1, 1 and 0. Similarly, the fourth atom, if I take it, this particular atom, are we moving anything in the x direction? There is no movement in the x direction. So that will be 0. In the y direction complete B, complete A, that is moved. So 1 unit you have moved. And then in the z direction there is no movement. So the coordinate will become 0, 1, 0. Similarly, if I calculate it, everything I have tabulated for you. So similarly, the fifth one, so if I take it the fifth point, so that is the center, this is the center of the unit cell, we will be placing one body centered atom, isn't it? So if I see this coordinates, as this is the center, we have to, let us drop it, and then let us drop this, and this is this one. So what is this portion? As this is the center, so obviously this will become the half portion, and this will become the half portion, and this will become the half portion. So in the x direction it has to move by 1 by 2 and 1 by 2 and 1 by 2, and the coordinates will become 1 by 2, 1 by 2, 1 by 2, right? Similarly, 6. Atom number 6, where is atom number 6? And this is atom number 6. In the x direction, is there any movement in this direction? For the 6, there is no movement in the x direction, so that is 0. In the y direction, is there any movement in this direction? In this direction, there is no movement in the for the 6. So y direction is also 0. But in the z direction, there is a complete movement. So that is 1 unit it has moved. So the coordinates will become 0, 0, 1. Similarly, the 7th atom, if I take it, 7th atom, if I take it, where is the 7th atom? 7th atom is here. So it has moved, origin, it has moved by 1 unit. Now you see, this has moved by 1 unit, right? So 1 unit in the x direction. In the y direction, any movement is there? There is no movement in the y direction. So obviously it is 0. So there is in the z direction again, there is a 1 unit movement is there. So the point is, the coordinates are 1, 0, 1. Similarly, if I take it 9th, just before 8th, we will take the 9th. So 9th, as there is no movement in the x direction, there is no movement in the x direction. So here it is the same, right? It is 0. And there is a movement in the y, a complete y, the extreme end it has moved, one of the edge lengths. So there is, this one is a 1. And in the y direction, again it has moved by 1 unit. So the point coordinates is 0, 1, 1. Now at the end we will see the 8th point, the point 8. So for going to point 8, we have to drop by 1 complete unit in the z direction and the complete movement in the y direction, and we have to go back to origin, that is the 1. So the point coordinates will become 1, 1, 1, right? So we will get 1, 1, 1 point coordinates for the 8th. So this is how we will be specifying the point coordinates for all atom positions within this unit cell. Similarly, you can do it for simple cubic crystal structure, as well as we can try for face centered cubic structure as well. We can locate the atom positions within the unit cell for all the crystal structures, right? If you summarize, so it is important that it may be necessary that we may need to specify the point locations within the crystal structure, or it could be a direction. We may need to discuss about atoms positioned in the particular direction, or atoms positioned in a particular plane. So first, in order to represent all these atom positions or atom directions or a particular plane, so first we have to create a labeling convention for these point locations or directions or planes that need to be established, and that need to be in line with the coordinate system, and which will be having 3 indices or 3 numbers. So what is the basis? Unit cell will serve as a foundation for this in determining these index values. So we will be picking a right hand coordinate system which is having 3 axes x, y, z, that is positioned at the one of the corners, and will be considering edge lengths as the coordinates x, y, z in the 3 directions. Then the position of any point that is located within the unit cell, that is specified here in terms of its coordinates as the fractional multiples of unit cell edge lengths. The maximum value for this fraction could be 1, and it will be always less than 1, or whether it is equal to or less than 1. So we have seen 2 exercise problems as well, right? So that's all for today's class. So I have referred this textbook for providing this lecture. Callister textbook, Material Science and Engineering, an introduction by Callister, W.D. Callister. So thank you all for listening.
Thank you.